Welcome to our lesson on complex numbers. Our learning targets for this lesson are for you to be able to simplify square roots and also to work with complex numbers using different mathematical operations, multiplication, addition, subtraction, and division. So we're going to start out talking a little bit about the product and quotient properties of square roots. And basically, if you have a square root with a product underneath it, you can split that into two separate square roots. Okay, and we've talked about this before, so you can go back and forth. You can separate them or you can bring them together. And the same holds true when we're dividing. We can write them as separate square roots or we can write them under the radical as a single square root. So here are some examples with numbers just to kind of help you make sense of that. If we have the square root of 6, we can write that as the square root of 3 times 2 under the radical, which is the square root of 3 times the square root of 2. So just whatever makes it easier for us to solve the problem, we can use whatever form helps us to get to the end goal of solving or simplifying. So one of the things I wanted to make sure that I mention is remember when we're dealing with radicals or square roots, remember that we can never have a radical or a square root in the denominator, and something is not completely simplified unless there are no perfect squares still contained underneath that radical. So just a little reminder for you there. So let's jump in and look at some examples here of how we are going to go ahead and simplify some square roots. Well, using that property we just discussed, we could write the square root of 24. I could write that as the square root of 4 times the square root of 6. And we know the square root of 4 is 2. And the square root of 6 does not simplify, so this one will just simply be 2 times the square root of 6. All right, over on the right-hand side, number 2, I could write this as the square root of 18 divided by the square root of 25. And I'm going to rewrite the numerator as the square root of 2 and the square root of 9. 9 is a perfect square. Remember, we're looking for those perfect squares that we can take out. And so 2 is going to be stuck, but the square root of 9 is really 3, so that's going to come out of the radical. 2 stays under the radical because he doesn't have a partner, right? And the square root of 25 is 5. So that's the answer for number 2. I've given you 2 more examples here that I would like you to complete. Go ahead, pause your video, this is a good time to do that, and try those 2 on your own. So what happens if we get a negative number under a square root? Okay, we've not really encountered that, but we're going to start seeing that in our work. And so we have what's called the imaginary unit I. I is defined as the square root of -1. And so you'll see things like 6i, -5i, I square roots of 3. You could have real, you could have irrational numbers with I. And I think Calvin does a great job of Calvin and Hobbes both do a great job of giving us a little laughter with imaginary numbers, so I hope you enjoy the little cartoon. That's one of my favorites. So sometimes we have numbers that have both real and imaginary components, and they look like this. 1 plus 6i, or 3 minus 5i, 4 plus I squared roots of 3. This is where we call these the complex numbers. The real and imaginary parts are not like terms, they cannot be combined. So this 3 cannot be combined with the 5i. So things that don't have an I cannot be combined with things that do have an I. They are not alike. So in words, I've defined for you what a complex number is. Anything that can be written in this form, a plus bi. A is the real part, bi is the imaginary part. And some examples of what they look like. So when we want to go ahead and simplify imaginary and complex numbers, our properties of associative and commutative still hold true. Okay, those we can still rearrange and reorder or regroup them and still get the same answers or the correct answers. When we're adding and subtracting complex numbers, since we cannot combine the real and imaginary parts, we just combine the real parts and then we combine the imaginary parts. And we'll do some examples of that in some future slides here. So here's a couple of examples. We want to multiply these two pure imaginary numbers together. So I can regroup those and write that as 28i squared. Now here's the tricky part. Remember, I is defined as the square root of -1. So we have the square root of -1 squared, right? So I want you to make sure that you're not going to write this as a +1. Some of you would be tempted to square the -1 under the radical, and that's not what it means. So we have 28 multiplied by this thing. And when we square that radical, those are inverse operations, and the radical and the square completely drop out, right? So these are inverse operations and they go away, and I am left with what was underneath the radical, which is -1. Make sure that you understand that process right there, that whenever you have an I squared, it's a -1. So now when I multiply 28 by -1, my answer is -28. Over on the right-hand side, okay, the first thing we're going to do is we're going to get this negative outside of the radical and call that I. So do that for each of these radicals. So I have I squared to 10 times I squared to 15. Well, that gives me an I squared times the square root of 150. Remember, we can bring those together. And there's a 25 in there. That's a perfect square. So we know I squared is -1. And we're going to write 150 as 25 times 6. And we know the square root of 25 is 5. So I get -5 square roots of 6. Here's a couple of examples where we add and subtract our complex numbers. So remember, we said we're going to just add the real parts and add the imaginary parts. So we're going to take 6 plus 1 gives us 7. And -4i plus 3i is -1i. So we get 7 minus I. Over on the right-hand side, we're going to have 3 minus 5. And then we're going to have a -2i minus a -4i. So they factored out the I here, and they did -2 minus a -4. Well, that's going to become a +4, which will give us a +2i. So remember, these do not combine, they stay separate. Here's an example. Find the values of x and y that will make this equation true. So when we look at this one, the thing I want you to recognize here is this right here is the whole real part, right? And so that will be set equal to the real part on the right. And then the other part here, this is the imaginary part. This is the b, a plus bi, so that will be set equal to the 2. So let's go ahead and set that up. So the real part, we have 2x minus 3 is equal to 3, and the imaginary part, we have y minus 4 is equal to 2. And now we can just solve those independently. Adding 3 to both sides, we get 2x is equal to 6, or x equals 3. Adding 4, we get y equals 6. So those are the values of x and y that would make that a true statement. If we want to solve a quadratic equation now, we're going to move on from graphing to solve into some algebraic methods to solve our quadratic equations. So one of the things I can do is I can subtract 48 from both sides and then divide by 3. So I get x squared equals -16. Now when I take my square root of both sides, we're always going to have two values here. We're going to have a positive and a negative value. And remember, this negative right here is going to come out as the letter I. And so we'll have I times the square root of 16, plus and minus I square roots of 16. And the square root of 16 is 4. So x is equal to plus and minus 4i. Here's an example from electricity. Where do we use these complex numbers? Well, in electricity, they usually use the letter J instead of I, so they don't confuse it with I in electronics is considered current. So they use the letter J. So just keep that in mind, that that means the imaginary unit for us. So this one says in an AC circuit, the voltage is E, the current is I, and the impedance is Z. And they are related to the formula E equals I times Z. They want us to find the voltage, which is E, look for E, in a circuit with the current, so this is I, and this is Z. Okay, so we're just going to plug those into our formula. So there's I and Z. Well, now these are two binomials, so we're going to use FOIL to multiply those. And so we do the first outer inner last, and our outer inner will always combine here. So we get 7 plus 16j minus 15j squared. Now j squared is -1. Remember, that's really like I squared. And so then this last term and the first term will combine. We'll have a plus 15 and a plus 7, which is a plus 22, plus 16j. Now keep in mind, one of the things I want to mention as well is we're always going to write this with the real term first plus the imaginary term. So this is like the standard form. This is your real part and then your imaginary part. Dividing complex numbers. When we're dividing complex numbers, we've talked about this before, we're going to be multiplying by the conjugate, okay? And this is called the complex conjugate. So that's a term you should be familiar with and be able to identify what the conjugate is. Since it's a complex number, we call it the complex conjugate, and we've done some work with conjugates already. So you're only looking at the denominator, and we want to multiply by the complex conjugate of the denominator, which is the same coefficients but a different sign here. So we're going to multiply the top and bottom by that complex conjugate. Okay, so we want to put parentheses around these. And when we multiply the numerator, we're just using the distributive property. Denominator, we're using FOIL. We end up with 6i minus 12i squared. Okay, and you should recognize this is going to be a -1 right here, so that's going to change this sign. And the same thing in the denominator. Now you can't cancel between anything here in the numerator and denominator just yet, so hang tight on that. All right, and so go ahead and substitute for I squared the value of -1, and you get 6i plus 12 divided by 4 plus 16, right? This is going to be a -1 times a -16 is a plus 16. And now we can actually, since we have a single number, we can divide each of these out. So what they're going to do in this one is they divide each of those out and they reverse the order. So they took 12 over 20. I'll just write that out for you here. So we have 12 over 20 plus 6i over 20. And if you reduce these, that's where these numbers come from. Okay? They just switch the order on you. So 3/5 plus 3/10 I. This is in that a plus bi form. Right over on the right-hand side, this one we only need to multiply by I to get rid of that complex number. When we do that in the denominator, we get 2i squared, and remember I squared is a -1. So our denominator turns into a -2. We got an I squared up in the numerator as well, so that became a -1. But we're going to reverse the order on this. We want the real part first, which will be a +1/2, and then we'll get minus 5/2 I. Here is your lesson check. I would like you to complete these before you come to class. So please take some time to try these on your own and then come to class with questions. See you next time.